Good afternoon and welcome back to this semester's edition of the Joint Astronomical Colloquium of Heidelberg. As you have seen in the announcement that I have sent around and that you see in the posters, we have quite an interesting suite of topics and speakers that covers the breadth and width and depth of modern astrophysical and astronomical research, so please come. We start this lecture series with Henk Hoekstra from the Sterrenwacht Leiden, who will be starting with the large-scale structure of the universe. He will explore weak lensing and what we can learn from weak lensing about the large-scale structure of the universe and much more than cosmology. So let me just briefly introduce the speaker to you. Henk did his PhD at the University of Groningen. He finished there in 2000, then moved over the Atlantic to Canada. You were a CETA fellow at the Canadian Institute of Theoretical Astrophysics in Toronto. Then he moved to the other side of the continent to the University of Victoria to take on a professorship there. And in, I think, 2007?
2008.
2008, yes. He went back to Europe to take a faculty position at Leiden University at the Sterrenwacht Leiden. He has a number of prestigious awards and fellowships. For instance, when he came back, he was awarded the Vidi grant of the Dutch Astronomical Wetenschaftliche Society. He also has an award from the European Research Council and many other things. So let's give science the word and let's welcome Henk Hoekstra.
Thanks. Well, it's a pleasure to be here, and I'm happy to talk about the work that I spend most of my time on when I'm not doing committee work and planning stuff. And so the talk is really indeed about what can we learn about large-scale structure using weak gravitational lensing, but it's also always nice when you have these data to do other things with it. But the main motivation for my work is really trying to answer this question, like who ordered this, right? This is the pizza that nobody ordered. And in popular lecture, I like also to say, like you go to a store where you buy a cheap pizza, right? If the students here, they might recognize this, right? And you buy this cheap pizza and it says exactly how much E126 is in there, but it doesn't tell you what the pizza is made of. And we sort of have the same problem in our universe because thanks to tremendous progress over the last, like roughly 2-3 decades, we now know how the pizza has to be sliced, but we don't really understand what these ingredients are. And I think that is really a difficult situation to be in and how to make progress. So on the dark matter side, which of course has been around for quite a while, we don't really know what it is, and there's a lot of activity going on, but sort of the main view is that it must be non-baryonic. I think that specifically the CMB has shown this, that it must be a non-baryonic new particle, so that's exciting because it means there's new physics, and also other measurements of large-scale structures sort of indicate that it must be a relatively cold or non-relativistic particle. So in this view, well, this cannot be standard model, there must be new physics, or people say, well, gravity is all wrong, which is also fine because it also implies new physics. So that's sort of a nice situation to be in. We know there's stuff to be discovered, we just have no idea what. But of course, there's many ideas. But in a way, dark energy, right, is much more problematic because at least for dark matter, there are ideas that have been around for a while, like what this could be. But dark energy, well, again, there are some ideas, but none of them are really satisfactory. So could it be a cosmological constant, which is in a way natural, but why is it so small then? Is it a dynamic field? Is it really a problem with general relativity, although it's becoming more and more difficult, for instance, with the gravitational wave detection of these merging neutron stars, which wiped out a whole range of parameter space. But the real problem is that we really lack a theoretical framework that sort of says, okay, this is how it is, right? Eventually, hopefully somebody will come along and says, this is how it is, and everybody's like, of course, but that hasn't happened yet. And so the approach I've taken is to basically say, well, then we need better observations to limit parameter space, and the hope is that eventually, by limiting things enough, that basically it becomes clear this is probably the right direction we should take. Right, and if you've ever been in the Netherlands, they have these little tiles with pieces of wisdom, and well, this is one I made myself. There's a website you can do this, but I think the quote is really nice because that sort of states the problem we're facing when we want to study the dark side of the universe. And the hardest thing of all is to find a black cat in a dark room, especially if there is no cat. And that's really the challenge, because we lack the theoretical framework. Like you have to be careful. We can design an experiment that measures something really well, but actually it measures the wrong thing. So we would draw the wrong conclusion because we got the physics wrong because we don't understand it. And so this is really the challenge when you try to do the next stage in cosmology. We know sort of the ingredients of the pizza, but how we really need to get to the nature of these ingredients is a bit trickier. Now, we can sort of ask, okay, what can we study? What should we study? And so clearly we want to study things that are sensitive to dark matter, modified gravity, and dark energy, right? So we want to, like, clearly, if we want to study this, we should be sensitive to this. And I think that's very important, you have to be able to measure these reliably. Because whatever, right, there's a reason why dark energy was only discovered in 1998, so 20 years ago, because the effects are so subtle. And to go a step further, we're now looking for extremely subtle deviations from a subtle effect. Now, so the discovery itself is essentially based on by looking at the cosmic expansion history, basically by measuring how that changes, and that's typically quantified by the dark energy equation of state, a W as a function of T. But another way to look at this is to look at the cosmic history of structure formation. So how does basically what gravity pulls things together while the universe is expanding? So this essentially cosmic tug of war leads to growth of structure formation, and the growth rate of structure formation measures sort of a mix of this expansion history and gravity. So by measuring the expansion history alone, you'll learn nothing about gravity, whereas by looking at cosmic structure formation, gravity enters the mix. Right, so that's basically showing how far we've gotten in the last 20 years on the supernova front. Right, these are the measurements of distance as a function of redshift from a whole suite of supernova surveys, and this is really tremendous progress, really demonstrating the need for dark energy or a cosmological constant. It's perfectly consistent with that, but there's a whole range, and now these measurements extend to fairly large redshift, so it's clear that the universe is accelerating its expansion. But as I said, like, this really is limited, because you can come up with whole classes of modified gravity theories that fit this and completely fail at a large-scale structure. And I think that people should not be allowed to do anymore. Right? It's basically people sort of say, here's my modified gravity theory, it fits the supernovae, we don't need dark energy. No, that's your first test. If you fail this test, then your theory is false. But you also need to test the other cosmological probes. You can't just claim victory by ignoring the very thing that your theory should make predictions about. If you change gravity, you should test basically how structure forms in the universe. And there are examples of theories where basically they predict exponential growth, which is clearly ruled out. Right? So these are exponentially, these are so ruled out by so many sigma that people can't even plot them. And so it's really important to keep that in mind, that basically cosmology is a whole coherent picture, and you can't just cherry pick your observable. But as I said, like, I want to focus on the clustering of matter effectively as a function of scale, so basically different scales, and cosmic time as redshift. And this is an example from two simulations where they look quite similar. The statistics are similar at low redshift, but one has no cosmological constant and the other one has a cosmological constant. And the net result is that their evolution is different. So even that a slice at a given time may look different, they will look different at different cosmic times. And so you can look at this and try to compare this to the data and say, okay, what's the correct theory? What's my correct model, parameter, and test gravity? Now, you can look at the distribution of matter with a variety of techniques. Some have been around for quite a while. So the popular topic is the clustering of galaxies, because these galaxies, they correspond to the peaks in this matter distribution, right? Because the baryons are pulled in. You can also look at galaxy clusters, which are sort of the most massive halos in the universe. But one of the challenges there is that although they trace the dark matter distribution very well, the mapping may not be perfect. For instance, we can fly over the Earth at night and fly over North America, and what we see is very nice. We see wherever there's light, we know there's many people, right? So the distribution of humans and light is highly correlated. And so we can use the light distribution to figure out where people are in North America. We can continue flying over Asia, and exactly the same. Wherever there are people, there's light, except there's an underlying parameter, in this case wealth, that actually sort of makes this more complicated, because although light clusters the same way with the distribution of people, the amount of light is different. There's additional parameters. Now, luckily in the universe, it's not that bad, but we have to be careful. So the amplitude of this signal, so even though the pattern is preserved, the amplitude itself depends on other parameters. And the same is true in the universe. So this is why the pattern of baryon acoustic oscillation is a very good probe of cosmology, because it actually, as a pattern, of course, there's modifications, but as a pattern, it's much simpler to understand and to predict than the amplitude of the signal, which depends on galaxy formation. And so galaxy biasing really makes the interpretation of clustering measurements just from out of the box very difficult. Of course, there's a lot of work going on to improve this. But we can see the clustering of matter by looking at, and that's the focus of this talk, by the fact that space-time gets distorted by massive structures, and what light rays then see is basically a curved space, and the net result is that you basically change the shapes of these distant galaxies. And so you basically get correlation in the shapes, apparent shapes of these galaxies, and we can observe this. So this is sort of highlighted here. So if you're close to a cluster of galaxies, this distortion is so large that it overwhelms the intrinsic shape of galaxies. But the regime where we're looking at, blown up here, these galaxies look completely random on the sky. But each one of them has a slight, is stretched in a slight, in roughly this direction, roughly tangential to the gradient in the gravitational potential. And if you average all these galaxies together, you find that on average, they have a preference to point in that direction. So an individual galaxy doesn't give us much information, but if we somehow could average many, many galaxies, and future experiments, the aim is to sort of average of order 2 billion galaxies, while square root of n still works. So basically by averaging so many galaxies while systematics are under control, because that's the tricky bit. So we need to be sure that we can average things. But if we get a high density of sources, for instance, with Hubble Space Telescope data, we can literally make an image of the dark matter distribution. So these distant galaxies, their light rays are distorted, and we can measure this coherent change in the shape of these galaxies, and we can use that. So basically it measures a tidal field, and the tidal field can be inverted to measure the projected mass distribution. So you've probably all seen this picture of the bullet cluster, where in blue you see the reconstructed mass distribution, which is different from the hot gas, and this is another cluster we've looked at. So this really shows that you can map the dark matter distribution in principle directly. And you don't have to look at clusters of galaxies. You can also just say, let's just look at a random patch of sky, and I could make a mass reconstruction. In reality, we don't do that, but essentially it's equivalent, so that graphically sort of gives you the same idea, where you can look at the distribution of this mass map and look at its statistics. But what we measure are these correlations in shapes, and you can sort of see that if you have galaxies distant in the universe, and for the moment, so in this talk, I essentially assume that there are no intrinsic correlations, because there are things due to galaxy formation, intrinsic alignments, and we know they exist. more or less subdominant currently, and there's a lot of work going on to really quantify this, to understand this. And there's also an interesting connection, well, that's the first and more for this talk, but it's interesting connection to galaxy formation, right? Like, how do galaxies get their spin is one of the oldest problems in galaxy formation. And it's still not really solved because the effects are so subtle, but thanks to these lensing surveys, we'll probably make a lot of progress on that. But let's assume they're randomly oriented as their light rays pass through the universe. And this is from an old publication in Nature, where I guess the illustrators are biologists, so hence the rather biological nature of these filaments. But as they pass through the same structures, they basically get stretched the same way. And the net result is that by the time we observe these, we see correlations in their shapes. Right? This is, of course, grossly exaggerated. In reality, the changes in shape are just invisible to the eye, of order 1% or less compared to a 30% intrinsic shape of galaxies. But we can measure this, and when we measure this, we can use this to infer cosmological parameters. Now, the problem is that we measure everything in projection. But there is a trick. If we now know how far away these sources are, we can use that to sort of reconstruct this. And again, this is more the graphical view. This is not what we do mathematically, but the graphical view is that basically you could think of constructing images of the dark matter distribution at different redshifts, because the low redshift galaxies only are sensitive to the dark matter at low redshift. So you can use those to sort of infer your low redshift mass distribution. The high redshift ones see the low redshift and high redshift mass distribution, but you've already reconstructed the low redshift one, so you can sort of subtract the low redshift version and sort of build up over cosmic time how the structure grows. And so for that, we need to have photometric redshifts, because these galaxies are typically too faint to get spectroscopy. So we really rely on photometric redshift to slice our samples. But actually, it turns out that is fine for lensing studies. So we don't need very precise redshifts. However, we do need accuracy. And people often say, well, we're now in this era of precision cosmology. And well, that's true. But that's very easy, because precision, and I always have to correct also my students, there's a difference between precision and accuracy. So it's good to spend some time on that. Precision cosmology means you have a big survey. It says nothing about how reliable your results are. You only have a lot of data, and so your statistical uncertainties are small. But what we want, and that's much harder, is accurate cosmology, because that means that you have very good control of your results. Basically, that your biases in the measurements are smaller than the statistical uncertainties. Right? So if we measure the shapes of many, many galaxies, we said we want to average all these shapes together so we get a meaningful signal. So accurate basically means that you get a meaningful signal. And so we need to make sure we can measure this very, very well. Also, we need to make sure that these photometric redshifts that we measure are sufficiently unbiased so that we get that we interpret the amplitude correctly. And so the signal itself, I already mentioned these intrinsic alignments. Right? They complicate the simple interpretation of the signal, because there's an additional source. If you view lensing as a weighing scale, these intrinsic alignments are the equivalent of, like, you put nothing on the weighing scale, but the dial is not at 0, but it's at some value. Right? So basically we need to correct, sort of say, okay, what's the correct weight of the universe? We need to correct for these intrinsic alignments. But there's also baryonic effects. Although I said this gravitational lensing is very nice and direct of the measurement of the mass distribution, of course, 16% of the mass is still baryonic matter, and that gets blown away by AGN feedback. At least that's the thought, that if you look at galaxy formation, you need these energetic processes that redistribute the baryons. Right? And that's the problem, because we're sensitive to small-scale structure formation. These galaxies are too faint for large spectroscopic surveys, although this situation is improving dramatically now, thanks to large observing campaigns. And for the shapes, when you look at the shape in an image, basically the observational data have far more distortions. Now, I won't go into too much detail on the technical aspects, but you can read in our papers that we now can measure these shapes to sort of order 1%. So I won't go too much detail, and the same is for these redshifts. Again, we're taking a lot of spectroscopic data to calibrate these. But I want to actually focus on some of the results we're getting from these measurements. And in particular, I want to focus on this measurement of the kilodegree survey. And the current measurements basically, because what lensing measures is more or less the variance. So we measure how much mass there is and how much it fluctuates. And so we can have a little bit of mass fluctuating a lot, which is low omega matter, high sigma 8. Sigma 8 is a normalization. Or we can have a high omega matter, a lot of matter, fluctuating a little bit, a low sigma 8. And so what we're really measuring with current data is sort of this combination, sigma 8 times square root of omega m. And if you look at the measurements over time, so now you can take notes. Although I don't think Matthias needs to take notes, as he knows the subject very well. So these are the measurements over time. And you see that, well, error bars is shrinking, but at the same time, actually, the error bar hasn't shrunk as much as we'd think, because as we went along, we discovered new problems that have been fixed. And we're now, although, yeah, I think I'm quite confident now that we're reaching a stage where we understand things well enough that we're in this regime where we can do accurate cosmology, where we can actually, with more data, reduce the uncertainties. The other thing to know, and we'll come back to this, is this gray band here, which is the latest Planck result. And you'll notice that we're slightly below there. Now, KITS itself, it's a survey carried out with this telescope here. I'll show a zoom in. And the optical, it's a very good image quality. So it's basically a telescope built, so the VLT survey telescope, not the very small telescope, but VLT survey telescope. The PI is Koen Kuiken in Leiden. And actually, in the end, we'll probably do slightly over 1,000 square degrees, about 1,200 square degrees. In the optical, with very good image quality, and it's complemented in the infrared with a Viking survey that is completed. So we have 9-band photometry, which allows us to do these photometric redshifts really well. But so we're up there. So it's a 2.5 meter telescope, but under the right angle, it looks as big as a VLT. And the workhorse instrument there is Omega Cam, which is a light mosaic wide field imager. And it's been taking data, roughly square degree field of view. So in current era with hypersuprime cam, LSST, etc., this is our small camera, but it's still, it's the only instrument on the telescope, so it basically does observations all the time. So KITS is a large family, it's a large group of people, and I guess they should be updated, but the main places are Leiden, Edinburgh, and Bonn, and then on the sort of non-lensing side also Naples and Groningen. But in reality, it's spread all over Europe and more also the rest of the world. And to start, I wanted to start with some of the early results we've did, basically looking at overlap of the KITS data with the spectroscopic survey called GAMA. And the reason for that is because it allows us to study the connection between the stellar distribution, the light distribution, and the dark matter. And the reason for that is because that allows us to study some of these feedback processes, because they are, as I said, very important to correctly interpret the data. And so these early results really focused on that unique combination, which is actually quite nice. So we targeted first those fields, and now we're adding more area to do the cosmology. And so this is, again, where lensing can be quite helpful in providing additional constraints to models of galaxy formation. And in particular, we focus on galaxy groups, which we can study with GAMA. And the reason for that is shown here as a sort of from a simulation by Amandine Lebrun, where you can sort of say this is a complicated number, but this is essentially a measure of feedback. So how powerful is the feedback that they put in this hydrodynamic simulation as a function of halo mass? Now, very massive clusters, the gravitational potential, the gravitational binding energy is so strong that the AGN, well, it moves the gas around a little bit, but it actually doesn't do that much. So these measurements are more or less converging to what you'd expect in your sort of standard dark matter only simulation, maybe a little bit less. But as you go to the group scale, there the binding energy of this group becomes comparable to the energy output of, so basically the work done by the AGN. And so that's basically where you have this crossover where the AGN actually has a huge impact on what happens to the baryonic contents of those systems. And that's what you see in the simulations, that if you start playing with your feedback model with different AGN feedback models, you really see that you can dial up and down the impact of the feedback. And this is important because this lensing signal that we measure sees all the matter distribution. So if we interpret our measurements with a dark matter only simulation, we're implicitly assuming, I think these dark matter only simulations are cheaper to run over larger scales. So we're implicitly assuming that the dark matter is tracing, or the baryons trace the dark matter perfectly. But if the AGN feedback starts moving stuff around, we expect that on certain scales, basically you suppress the power because you're making things more random. Whereas, of course, the galaxies themselves, they become very condensed, so the baryons can cool, they become dense, they cause a spike in power. And that's what we see in dark matter simulation. So when we compare the power spectrum, so basically the fluctuations in a hydro simulation to a dark matter only case, then on large scales, nothing happens. On small scales, you see this huge spike up because that's the gas cooling, so basically makes stars, right? So that gas becomes very compact, so you get very strong spikes, so you get a lot of variance. And on this intermediate scale, it depends on what you're doing. But if you have AGN, basically you're removing the gas from the group, so you're suppressing the fluctuations on that scale, and you're moving it, you're smearing it out. And when you smear something out, you suppress the power. And if you now were to use this dark matter only simulation to interpret your data, this is work done by Elisabetta Cimboloni, then if you were to do a Euclid-like survey, a future space mission, you could completely screw up your measurements of dark energy parameters. Because that effect of dark energy is sufficiently subtle that these baryonic effects overwhelm the signature of evolving or dark energy parameters. And not only dark energy parameters, also omega matter. The neutrino mass is not too bad, but some of the other parameters as well. But you can try to use simple models, and this is work we're doing now, to sort of account for this, to try to put in our knowledge of baryon physics feedback to account for the changes in the matter power spectrum. And this has picked up really. This is now a major topic of research, which is nice, because when we first came up with this, it was a bit of a shock, right? Because we promised lensing was this clean probe of cosmology, and it turns out it's as dirty as any other probe. Although that's a bit too exaggerated, because as I said, we can use observations, and that's the big difference. We can use observations to calibrate these things. But still, more work is needed. So as I said, kids focus on these boxes here, the sky coverage of gamma. And this is the data we released as part of the 450 square degree survey. So I'll get to the cosmology bit. But gamma is very nice because it's a redshift survey done at the AAT with the 2DF spectrograph. But what is key is that when because you can't put the fibers very close together, is what they did is they made sure they kept repeating, putting fibers on galaxies close together, so they got very high completeness. So this is a survey that is spectroscopically complete down to magnitude, the R-band magnitude of 19.8. Right? If you look at SDSS, basically once things are sort of an arc minute apart, one of them only gets a redshift. Anything closer than that doesn't get redshifts. Only one of the galaxies gets redshift. Here they kept going back until they got pretty much redshifts for everything. And that allows us to identify groupings of galaxies at very low masses. So this is a unique group catalog that is superior to the Sloan group catalogs. At also interesting redshift that we can efficiently study using gravitational lensing. And so here you see basically what the redshift cone looks like, and you can sort of see the clustering there. And so when we combine these gamma spectroscopy with KITS imaging, we can find groups. So this is one of the more massive groups in the cluster. And so for instance, gamma tells us exactly which of these galaxies belong to the group, which is hard to do with just photometric redshift. So we know exactly, okay, these guys are part of the group, but we can also look at thermal SZ from Planck, and there's now also follow-up from ACT and SPT. But this gives us an image of the hot gas, the pressure, essentially. Or we can look at the X-ray observation, in this case Rosette observation. They're bright enough, so this one is fairly bright, that it also gets picked up in Rosette. And of course, in the hopefully not too distant future, eROSITA will sort of provide amazing data for pretty much all of this, although I'm not sure if this is in the Russian sector or not. And of course, we can look at lensing itself. So this is where we use the deep imaging of kits to complement this and basically make an image of the dark matter distribution. And you can sort of see that we can combine all these measurements, this multi-wavelength data, to study the scaling relations. And for the lensing, we basically measure, as I said, this tangential alignment as a function of distance, and it allows us to reconstruct the mass density profile of these galaxy groups. And we do this in an ensemble average weight because an individual group is just not massive enough to yield a significant signal. And so that's this delta sigma. So just for all practical purposes, this is more or less the surface density. And you can see that we're, as a function of luminosity of the group, so we just add up all the galaxies in the group, we add up all the luminosities, and we detect a very nice signal. When I did my thesis, basically we had a group catalog of, I think, 40 groups, and we had sort of this 2.5 sigma measurement, and it was like, that was state of the art. This is way, way better. So really shows how much better the measurements have become in the last sort of 15 years. And so we can do this as a function of group luminosity and compare also to other measurements. But what is more important is these measurements we can compare also to cosmological simulations. And so there we ran into an interesting problem that people that run the simulations and then plot their results, plot often results that are not measurable, like halo mass. We don't know the halo mass. And so we know that we've ruled out this ref simulation because we see groups there. But what we would like to have is our measurements, which are these points here, and predictions of those points. So what would have been more useful would have been the mean mass to light ratio of the group versus BCG luminosity, because that would have been an ensemble average property. We want to see average properties here versus things we can measure. And so this is a complication which only now is starting to be remedied, that we're talking to the people running simulations in Leiden and really make sure that we observe the simulations. And there's actually two reasons. So A, because we think that's quite useful to compare, to inform them if they're doing a good job. But also because the simulations, I would say, are now getting good enough and the data are good enough that such a comparison is meaningful. I would say maybe 10 years ago, we didn't have to compare to simulations to know that they would be wrong. But now they're getting pretty good. Like they're actually starting to match the data quite well, partly because they tune certain things, but they're getting interestingly good so that they're also informing us about what do we measure. And so a very nice data set is BAHAMAS, which we've started looking at with a master student, and a paper has been submitted. And BAHAMAS basically is guaranteed by tuning the parameters so that the stellar mass function is right, and it also gets the X-ray scaling relations more or less right. So that's quite nice. And so basically it matches key observations, which wasn't the case before. And so we ask the question, okay, that's nice. So we can find groups in BAHAMAS because it's large enough volume so that it actually matches the gamma survey and the KITS data. And we can ask, okay, what do you predict for the lensing signal? And here are two group samples with the lensing signal. So we run exactly the same code as we run on the data, we run on the simulation. It's a light cone. And in black, so red is gamma prediction, in black are our measurements. So that's pretty good. Of course, maybe not too surprising because they got the stellar mass function, but basically they set things up in such a way that also the relation between halo mass and stellar mass resulted in a lensing signal that is consistent with the measurements, right? And this will only get better. We also looked at the X-ray scaling relation, so that's much more tricky to do in the simulations, also because the measurements themselves may not be that well calibrated, but overall, we found also very good agreement. So these BAHAMAS simulations do capture the observations that we have, both stellar mass and X-rays, reasonably well. And And that's sort of the idea. So what we want to do is by looking at data and such scaling relations sort of home in on those simulations that match the data and then ask what's the power spectra of the total matter distribution of those simulations that match all these scaling relations. And that should give us priors on the impact of the feedback. Because right now we have to allow for a large range of physical models, but eventually we might be able to constrain these and put in informative priors on these feedback models. And actually, Stijn de Bakker, student with Joop Shea and myself, has used X-ray observations, and he's shown already that you can restrict parameter space, so that's good news, but he also showed that actually the key challenge is to understand the gas distribution, the outskirts of clusters and groups, because that's actually where the biggest uncertainties occur, and so that's actually something that's also still quite hard to measure. But this is really work in progress, but it's quite encouraging that we're making progress in sort of matching this. But back to the cosmology result. Right, so this is why we're trying to study these feedback models, but of course we're also trying to get the cosmology out given the data that we have, because a lot of the work on feedback is really needed for future surveys, but less of an issue for current generation. So the results that were published cover 450 square degrees for the period roughly 3 years ago, and we now have more data that we're working on. And so we made mass reconstructions of these fields, so people have been analyzing those, looking at statistics of peaks there, so it's a nice complementary probe. And compared to what we had done before, the COVC legacy survey, basically we improved almost on everything. The shape measurements were improved. Also the spectroscopic redshifts are better calibrated. Intrinsic alignments were accounted for. We included this baryon physics as well. And also very important development, which you see now broader and broader, like we're getting the error bars, like there's a lot of work going on, covariance matrices, which is non-trivial for these large surveys. And there's a very detailed paper, about 50 pages, that you can read with all the details. The key measurements are here. So these are these correlation functions of the ellipticities between galaxy pairs as a function of distance, and we split the data in 4 of these redshift bins. And these are the correlations like between bin 4 and bin 1. And so the diagonals are here, the low redshift ones up to high redshift. You see the signal go up at high redshift, and these are the cross correlations. And then we measure 2 correlation functions. So this is hard to interpret. What is more important to then say, okay, what does it mean for cosmology? And there it's another very important point, which again is now becoming more or less commonplace, at least in cosmology, is to avoid confirmation bias or defamation bias, right? You can either want to confirm that you agree with some big shot, for instance, Planck, right? The Planck mission has a very good measurement, or you say, I want to defame this result. In both cases, right, you're potentially biased. And so you have to make sure that you do everything possible to not bias your outcome. And so what we did is we gave our data to Matthias, or at least we gave some mechanism to Matthias to blind the data. And so basically we ended up with 3 catalogs, and we did not know which one is correct. And so we analyzed all of these, checked for systematics, checked for all kinds of things until we were happy. So I say, we're happy. And then we asked Matthias which one was the right one. Now, this was the first one, so blind number 1. And you can see here this degeneracy in cosmological parameters, what I mentioned earlier, right? We have the degeneracy. We can have a lot of matter fluctuating a little bit, or a little bit of matter fluctuating a lot. And so here, if we put this S8 parameter, you basically take out the degeneracy. And you can see here in green our measurements, 1 and 2 sigma. And here's the Planck measurement, and here's WMAP 9. So this had sort of a 2.3 sigma discrepancy with Planck. But who cares, because this is one of the blinds, and we shifted things roughly of order 1 sigma. So this is potential. Next blind could be completely consistent. Oh no, it's 2.8 sigma. And then the last one is 1.7 sigma. And so when this was first shown at the Euclid consortium meeting, Conrad then asked the audience, so which one is the correct one? And there we saw a nice example of confirmation bias, because maybe the Planck people in the crowd, they picked this one. But it's not. It's actually the first one. And it really shows you have to be very careful not to keep on tinkering with the data until you like the answers. We really, well, we still like the answer, but this is what was published. And about this is the error bar we're getting. And so this is at a level where I wouldn't worry too much, right? This is interesting, but, and is mostly statistical, about 25% we thought was systematics, mostly related to the photo Z's. But this, well, calls for further study, and that's what we started to do, and that's what we've been busy with for longer than we thought we would be. Right, but we really need better measurements, much smaller error bars. And we can do that two ways. So one way is actually improving, like this first result was based on just the optical data. We now have added the infrared data, so now we get much cleaner tomographic redshift bins. And instead of 4 bins, we can now add a higher redshift bin. So we now do 5-bin tomography. So that high redshift is really powerful. We couldn't constrain it before, but now we can do that very well. We also added a lot more spectroscopy. We had the luminous idea of actually observing spectroscopic fields, and that really increased the number of spectroscopic redshifts. And we're actually been fixing a lot of other things as well, and then discovered new things. And so that's why it's taken a bit longer. I've been spending now 6 months looking at CCD detector effects. Not so much that they're important here, but they might be important for future surveys. And we're about to start the analysis of the 1,000 square degrees, but we really want to first fix. So even though we're reanalyzing this 450 square degrees, our uncertainty should already improve. And then when we double the area, we're not improving by a square root of 2, but roughly factor of 2 because of this better tomography. And so we can add also something that we now see more and more also in the dark energy survey, add, for instance, clustering measurement to sort of improve the constraints. And so that's a very powerful way to sort of do multi-probe, look at galaxy clustering and galaxy-galaxy lensing to get joint constraints and really break degeneracies in parameters. So even though like this, there is a lot of work still going on to really make essentially progress on all fronts. And most of the changes are really small, but we still want to do a good job. And again, we're still doing this blindly. So we need to push things as far until we basically this is fine again, and then we'll release hopefully in the next month or so. So that's keeping me busy, but the other thing that's keeping me busy is the future, and in particular this object there. So the Euclid satellite. So that's ESA's mission to study dark energy, and it is really designed to do 2 things: galaxy clustering in the infrared and weak lensing in the optical. So it really gives you these very sharp images that we need to measure the very accurate shapes, right? And so we need to image a lot of data on the sky. So the Hubble Space Telescope, like we've used that for lensing studies, it's been very useful, but it just has a small field of view. And to just give you an idea of the Euclid mission, right? So like you've all seen these HST images, and HST has been up for about 25 years. All the data HST has taken in roughly last 25 years, we'll do in a few days. And then we'll continue for 6 years. So that's a lot of pictures. And that gives you the idea of how a single HST field compares to a single Euclid pointing. Right? So this is 1/60,000th of the survey. So this is really a lot of data. And essentially the image quality is a little bit worse than HST ACS. It's more like the old camera on Hubble, the WIFPIC 2 camera. So, but it's pretty close to Hubble resolution. And it's just about 2 billion galaxies. So it's lots of galaxies. And I think this is where we expect lots of discoveries to be made. And not only in the optical, this is complemented to get good photometric redshifts. So the other optical bands we do from the ground, but the infrared data is taken also from Euclid. And that's a phenomenal near-infrared survey of the extragalactic star to an B magnitude of about 24. If you want to do that survey from the ground, it would take you 600 years. It'll be taken in 6 years, and actually a lot of people, most of the people in Leiden are more interested in that. So the sort of other science that it enables, high redshift quasars, high redshift galaxies, etc. But of course, the optical data are also incredibly powerful for morphology studies. And so basically, if a gravitational wave goes off in the 1/3 of the sky that we observe, you'll have the reference image, and you can really see what's going on. And so the idea is that Euclid is like Sloan, that although it was designed to do cosmology, most papers will be about completely other things. But to end with the cosmology, to give you a flavor of sort of the old constraints, we're now working with Euclid on sort of getting the improved constraints, putting in all our new knowledge of assumptions, etc., that we make. But Euclid really pushes to the next level in dark energy equation of state. So that's a convenient way to parameterize things. Ultimately, you would like to do model comparison, but it's a good way to parameterize things for design to basically of order 1% or better than 1% when we combine with CMB measurements, right? And this will only improve with also better CMB measurements from the ground, other measurements, etc. So this is really going to go to sub% precision on the dark energy equation of states. And so basically that's the sort of aim, to either say this is a cosmological constant and we're going to do something else, like exoplanets, or we find that there's actually, it's something fundamentally new. But we have no idea which of the two it's going to be. Also quite important, we can test some of the early universe, like the spectral index of inflation and the growth factor, so basically testing modified gravity. So and again, we're going to sub% level of precision. So we're really testing things to a level where it's hard to really make a significant improvement afterwards. So either we discover something new, and we really need to think hard as what the next stage will be, or I think I for sure would give up on cosmology and sort of start doing something else, because it's going to be so difficult to, in my lifetime, whatever remains, to really change things. So it's really an interesting time to be in this field, actually, right? Because it's really like, on one hand, we have something really weird about the universe, but we really need to get these observations to see where we need to go. So that brings me to my conclusions. So I hope to give you a flavor of the work we've been doing and what can be done with weak gravitational lensing. So it's on one hand the cosmology, but there's interesting links to galaxy formation, galaxy evolution as well, which in turn we need to interpret our signal. Something I've also worked on is on calibration clusters of galaxies. Still a lot of work in progress as we move along. So we learn things by defining things for Euclid, which we apply to kids. And in kids' data, we discover things which we then realize we have forgotten for Euclid, so we put it back in. So there's a very nice synergy where you really see how one project builds on the next one. Similarly, like we benefit tremendously from Gaia. So several or many issues remain. It's sometimes a bit of a roller coaster, and you think you've solved everything, and then you discover something new. But it keeps us busy. It's clear that the data analysis and interpretation is complex. So we really need to focus on understanding. So I think I've been saying also to Jenny, like we're moving more and more into more like LHC-like setup, where we're focusing our effort on characterizing the instrument and forward modeling everything, and sort of say, okay, this is then the cosmology, because the data are becoming very complex. But the positive news is that so far we haven't found a showstopper. Thanks.
Thank you, Henk, for this very nice and stimulating overview of weak lensing and what the future with Euclid will bring. The podium is open for discussions. Who would like to start? Matthias.
I was wondering, Henk, do you need more data, or do you need a better covariance matrix?
Well, so the covariance matrix, so right now, you mean, or?
In particular, in view of Euclid.
So I think there's a lot of work on the covariance matrix. So I think that, well, we need a better covariance matrix than we have now, that's for sure. So people have done some naive calculations, and then you sort of end up of the order of 10 to the 6 n-body simulations, which is a bit much. But at the same time, there's a lot of work going on showing the correlate. Like the problem is, in the end, it's a physics problem, right? So that is taking this as a pure data problem that you don't know anything about the underlying model of structure formation. It turns out that you need this covariance matrix, at least on the small scales, because of nonlinear structure growth, but that you can sort of relate to one another. So you can actually play games and dramatically reduce the number of simulations that you need by looking actually what is actually changing. Like for instance, in particular, you get the fluctuations due to long wave modes. And so there's a lot of work going on. It's still challenging. So I think that's sort of an interesting development that indeed we're now really worried about getting the covariance matrix right, which is, I think, sort of new in large scale structure. We're piggybacking a lot on the galaxy clustering as well, but their situation is a little bit easier because they sort of look at large scales. But again, I think there's a lot of work going on, and I think progress is such that it's becoming quite feasible to do this. Gets more complicated if you start putting higher order statistics, but at least for the 2-point statistic, I think it's okay.
Can I ask about the time coverage, the cadence with Euclid will cover certain fields? How well can you do time domain astronomy?
Essentially none, unless you're interested in things that change in an hour. Yeah, so we basically do the whole survey. There is a deep field, so we have sort of two deep fields, one in the north ecliptic pole and the other one somewhere in the south. South ecliptic pole was taken by the Large Magellanic Cloud, unfortunately, so we can't look there. At least for calibration purposes, it doesn't make sense. And so they will be built up, but it's a sort of strange cadence. So we have talked, and it's a sort of, so we do the 6-year survey, and afterwards, if in principle, things might still be working. So you could do a supernova survey. So people have talked about doing a supernova survey, or actually a microlensing survey is also an option. But they have to be pushed towards the end because radiation damage degrades our detectors. But in principle, it's possible, but not in the main survey.
If I may, I would ask another question. You advertised these BAHAMAS simulations, and I was wondering what the feedback model was like that you put into that.
It's the same as what was used for OWL. So the same. What's his name? One of Joop's postdocs that they put in. But they played with the amplitude so that so it's the same feedback model, but you play with the parameters so that you get the scaling relation, the X-ray, and the stellar mass right. So for instance, so Eagle, sort of, they did also the scaling for the stellar mass, but it doesn't get the X-rays right, and it's also smaller to small volume. And that's also the tricky thing. So this is where it's tuning, right? It's not really physics, because if you start with Eagle and you scale up BAHAMAS is lower resolution, then it turns out you have to change your feedback parameters. So there's a talk between us. I mean, it's really subgrid. But for my purposes, that's perfectly fine, because I'm interested in sort of the overall properties, not the microphysics, but ultimately, like, that is where they want to go. And so you're now seeing this sequence of simulations.
So we could call this an effective model calibrated on a wide scale of observations.
Yeah, and so then the open question, I think, for the future, more for Euclid, is what do they say about the gas distribution at sort of R500 up to the virial radius? Because that's where the biggest uncertainty is now, because observations are really difficult. So what we did with Stein de Bakker was not very physical, but we sort of did a sensitivity analysis. But the hope is that eventually these models will all sort of give more or less consistent results. We also don't know exactly how well this needs to be done. But yeah.
So Björn is the next question.
Henk, I would like to ask how much you would expect from higher order statistical measures of the weak lensing signal, in particular because they are not easy to quantify, and their covariances are unknown, and their distribution functions. So I would be interested in your view.
Yeah, so I think that's where I can put on my other hat in sort of cluster cosmology, because there's a paper by Takada and Spergel where they sort of say, well, you can do cosmic shear 2-point statistics up to L of few thousand, and then you can look at cluster, so essentially peak statistics, and then you recover most of the information. Now, the peak statistic itself has its own issues, but that might be a more effective way to do this. Although, again, things like selection function can be problematic. So it's not completely clear, but I agree that 3-point or higher order statistics are really difficult to deal with. And so then, in a way, dealing with just the peaks themselves is much more contained, might work. It's actually, because that's what causes most of the issue in the covariance. It's basically how many clusters do you have in your simulation, and so that clearly captures also most of the variance that you have. So once you do clusters and cosmic shear, you probably got most of the data, and then the question is how much time you want to spend to get another 5% out of the data.
So far, your weak lensing surveys are confined to the younger half of the universe, like this must say that you showed is 6 billion years or something.
Yeah.
Whereas the other half would be more interesting. So to what depths could you go with Euclid and the forthcoming missions?
Yeah, so the problem with lensing is that you're looking at roughly the stuff between the source and the lens. So we're sort of stuck at low redshift. Although this growth of structure does have a sensitivity to higher redshift tails. And so in particular, high redshift clusters, like if you can calibrate their masses and look at their abundances, they might contain some information what happened early on. But I think really high redshift, I think future survey is more like H1 intensity mapping project. They really can probe the clustering at high redshift where things are still linear, because early on things get simple again, but right now we can't see it. So this, in that sense, yeah, is a sort of intermediate stage, but it's really, yeah, indeed low redshift. Unfortunately, we can't do much more than that.
Henk, you indicated that Euclid, although originally conceived as a cosmology mission, will affect many branches of astrophysics as well. So what is the data policy for the publication of data?
Well, so there will be 3 data releases. But is there anybody here who's not a member of Euclid? So I think, really? No, yeah. So Euclid has a lot of people involved. And so, but so within the consortium, we actually take a more Sloan-like approach, so that there's some cosmology projects that are sort of clearly defined, actually in the process of defining all these things. That's also fun to do. But there's also just people can propose projects. So we basically look, there's tons of other things people can just propose, and so that people know, okay, you want to do this, you want to look at a particular NGC galaxy, do stuff, you can just do it. Of course, you have to pass by Peter Schneider, who is the editor. So things get properly reviewed, etc. But it's quite open when you want to do stuff. If you're outside the consortium, yeah, there's the 3 data releases. So sort of the 1 year, there will be also some intermediate like teasers, sort of stuff, see how nice the data are. But the first year data will be sort of, I think, roughly 3 years after launch. And then half the survey, sort of 5 years after launch, is roughly those numbers, I forget the details. And then sort of a year after the end of the survey is the final data product. So it's Sloan-like, where initially internally people can do stuff, but also the internal thing is very open. So it really is to encourage. It's also only the what we call flagship papers are completely alphabetical, but all these standard projects are like Sloan is just first author papers with, of course, some people included on to recognize their contribution to the data themselves. But we take Sloan as our example, not Planck.
Okay.
Well,
You want to join?
would I do this here? Hey, could you go back 2 or 3 slides? I don't know where you show the combination of probes.
Yeah.
Stop. Yes, this one. Is isn't it suspicious that all the other probes move the likelihood upward?
Well, no, so this is, yeah, so this is really, it's mostly this one and this one. So these are two independent. This is galaxy lensing and galaxy clustering, and this is the cosmic shear, and they are consistent with one another. So it's true that it moves it to the middle, but essentially they are consistent.
Okay, so you wouldn't attribute any significance to them.
So this is what you, it would be really bad if, well, it would be interesting if it would be below, but if they would be right on top of each other, we would be very worried, right? This is what you'd expect with noise. And that's sort of, as I said, like, this is interesting, but we really need just improve the error bars or reduce them.
So I see no more questions. Before we thank Henk again for this very nice talk, let me make 3 announcements. The first one is to next week's talk by Leiden from the University of Stockholm, who will go to much, much smaller scales. He will talk about the chromosphere of the sun and the very detailed calculations and physical models that are available to describe this interesting feature that beautifies our days. Oh, sorry, in 2 weeks, yes, absolutely, sorry. Next week is May 1st, and of course, we celebrate the May holiday. Thanks for these corrections. Then, as in the past semesters, there will be the opportunity for the PhD students and postdocs to meet with the speaker over drinks, and this is organized by Thomas Greif. So if you're interested, just come down here and then you go to probably the Neuenheimer Marktplatz, which is very nice on the sunshine day. Finally, there is then the dinner with the speaker at 19 hours at 7 o'clock. And because the weather is so nice, I would say, meet at the Neuenheimer Marktplatz. Or if you want to sneak out, let me know, then I can send you an email where we are meeting. With that, many thanks for your very nice